Okay, I think this is where we left off. Are you ready?
Not really.
Are we going?
Yes.
Okay. Hund's rule. As a quick recap, we talked about the outfall principle. We fill from the lowest energy level first. We talked about the Pauli exclusion principle. A maximum of 2 electrons per orbital, and those 2 electrons have to have opposite spins. And now we're going to talk about our third rule, Hund's rule, that says electrons don't double up until they have to. Yes?
How can two things have different spins? Because if you just look at it a different way, it's spinning the same way.
Well, that's why we're saying opposite spins. That's in comparison to one another. Because if we have 2 items spinning in close proximity, we can tell if they're spinning the same way or if they're spinning opposite.
But if they're like spherical, then if you just look at it a different way, it's spinning the same way.
Not if in relationship to one another, they're both spinning in opposite directions. Doesn't matter what our point of reference is. Whatever point of reference, they're spinning in opposite directions. Because if I change my point of reference for one, I change my point of reference for the other.
Okay.
How do they both spin in opposite directions besides they crash into each other?
Well, they're not like spinning like we're rotating on our axis. We're talking about a rotation against an axis.
So like they're spinning.
We're talking about spinning like a top, you know, like it's sitting right here, like a gyroscope, spinning right here. One spinning here, one spinning here. They're not going to run into each other because I'm not talking about going in an orbital. I'm talking about spinning around an axis.
Even though they're spinning differently, they still go in the same direction.
No, they're going like this.
They're in
No,
orbitals.
but like
They don't move like
with
that.
the orbitals.
We're not, this isn't about orbitals. This is about the spin of the particle about its own axis. Just like we're spinning around our axis and like we're going like this. Do you agree?
Yes.
Like that's what we're doing right now. Okay, so let's practice with phosphorus. If you look at phosphorus on the periodic table, it's element 15, correct? So when we're doing electron configurations, we're writing in electrons. You're going to find out lots more about this in the next days. This is an outfall chart. And if you'll recall, we fill from the lowest energy level up. So when we're looking at making, this is called orbital notation when we use these boxes. I'll talk more about that in a few minutes. The first orbital to fill up is the 1s. Do you remember this?
Yeah.
And I designate my electrons with an up arrow and a down arrow. All that indicates is that this s orbital is full. According to Pauli exclusion, it can only hold a maximum of 2 electrons. And according to Hund's rule, they have to have opposite spins. No, that's still Pauli exclusion. They have to have opposite spins. Hund's rule says they have to have one. We put one up arrow, and we put a down arrow. That's easier to see when we get to our p orbitals. So we need to get up to 15. What are the next 2 going to be? Where are we going to add those? We're going to add 2 in the 2s. And we're up to 4. What's next? We're going to put our 6 into our 2p. Now I've got 2, 4, 6, 8, 10. And I want to talk about the p sublevel. Look at the p sublevel. For orbital notations, I always have 3 boxes listed for any p sublevel. Do you recall that there's 6 electrons from left to right, from boron to neon? And I'm going to have one of my p orbitals located along the x, one along the y, and one along the z. Do you remember that? So there's one, my x, my y, and my z. And each of those can hold a maximum of 2 electrons. And now we're up to 10. Here we're up to 12. How many more do I need?
3.
3. So you don't write this, oh, I'll take that out. Do not do this. That's wrong. What does Hund's rule tell us? Yes.
They don't pair up unless they need to.
They don't pair up. You have to put one in each. I do half arrows. You do one in each before you double up. This is very important because it talks about, we will talk about later, unshared electrons and their very deep desire to pair up with something. That's why compounds form. It's why we get hybrid orbitals. There's a lot of things that will come up from that. So when we put these three in, that's what they look like. I'll erase mine. That's what that one looks like. Now, that is our orbital notation. And if you will take a little glance at that sheet with 8 things on the front and 8 things on the back I just handed you, there's a spot there for orbital notation. I just want you to locate it. On each one of those, do you see that there's a spot for orbital notation? So this is what we're talking about. FYI, once you have this down, just don't sit and do them for fun, unless you like really love doing them. But once you have these down, you don't have to do these for each and every element we're going to practice with. If you get mixed up, do these. We have 3 unshared electrons, unpaired electrons, and this, 1s2, 2s2, 2p6, 3s2, 3p3 is our electron configuration. Very quickly, let's race. What do the superscripts add up to? You shouldn't even have to do it because we were doing phosphorus. Who already knew that? Really? 15? Okay. Do you have questions for me about this one? Yes.
So, do the degrees of each of the bottom, like the 1s to the second, does that mean just 2 electrons?
Where are you talking?
So, in the final answer, the 1s squared.
That we don't think of that as squared.
Okay, so we just
That's
think
going to
of
be
it
a
as
2.
electrons.
Can you grab the door? And a 2. That's why I call them superscripts.
Okay.
Because that indicates a number of electrons in this case, not a squared or to the 6th power. So this is a different application of those superscripts. All those indicate is the number of electrons. It's not raised to a power. Yes? Wait a sec. They're taking a test today, and I mean. They go kill at the end.
Yeah.
Nope, they're not going to do it. Okay.
You're gonna have to memorize the alpha.
Yes and no. You don't have to ever memorize it because you're going to find as we do this that it follows along in exact order of your periodic table. There's nothing to memorize.
So we'll always have the periodic table.
You will be given the periodic table, the one, and if you want to take yours out to look at, that's great, but the same one as yours is the one that I have laminated that you get to use on all assessments. Okay? Okay, any other questions on this one? Okay, and this doesn't work, that link doesn't work. Okay. Every element, the most stable column of elements on the periodic table is this one right here, the noble gases. Each one of those, except for helium, has a P6. P6 is as stable as it gets. Adding electrons can change your energy. Full orbitals are what everything wants to be. If you can't have a full orbital, if you'll recall, when we were doing phosphorus, each one of the p orbitals had 1 electron in it. That's a little bit more stable than if you have only 1 or only 2. So half-full are a little bit more stable. When we do our next unit, you're going to get a lot more information of this, but to figure out some of our exceptions for electron configurations, we need to know this. Half-filled is a tinge more stable and it changes the filling order. Yes?
Did you already go over why they were more stable?
The only reason they're more stable is, I'm gonna put a D sublevel up here. Remember, this is orbital notation,
Yeah.
and if you recall, the D sublevel has 10 elements from left to right, from scandium to zinc. So I put 5 boxes. So when I fill these, when I start filling with the electrons, I put the first 5 in, and then I achieve like a little pseudo stability after I have 5. Because if once each one has one, they just go to a lower energy. Everything wants to go to a low energy, a ground state. And when these all have one, they're a little bit more stable. Does that make sense to you?
Yeah.
I'm gonna leave this up here because we're gonna see that in a moment.
Also, do they have to be up arrows or can you put down arrows?
The convention is start with up
Okay.
and then downs.
Alright.
That is the way everybody has ever done it that I have ever seen.
Sorry.
Well, I'm just telling you that I've never seen it done another way. It wouldn't be wrong because the electrons don't know whether it's an up arrow or down arrow. But yes,
Why is
Yeah,
half filled more stable than one side of half filled? 'Cause wouldn't
it
that be-
just has to do with, the orbitals exist whether there's electrons in them or not. So you've got your 5 p orbitals, and we're gonna look at those in a few minutes. You've got your 5 d orbitals, and once you put 1 in each, then those orbitals basically have a purpose. And then we can double up. They like it better when there's 1 in each, 2 in each one.
Alright, so would like 75% full be more stable than
no.
50?
No. Just half full, which means 1 in each orbital.
So at half full it becomes a certain amount of like level of stability, and then the stability doesn't go up again until it's all the way full.
You're correct. Next unit, this is just a preview. In the next unit, we're going to do a lot of trends on the periodic table. And we're gonna graph different trends that are very visible in the P sublevel, where they'll go up for the first 3, and then they drop, and then they go up again. Because we hit a half full orbital, it's stable, and then it has to work up to a full orbital again. You're gonna see a lot of trends when we do periodicity. Okay, would you do me a favor? On your marks, get set, titanium, go, let's race. Titanium is 22. Two, 3D2. Okay, who was already done? Did I win and I didn't start? Who is it? Who's done? You are? Did you get this? 1 has 2. 2 has 2. 2p6. 3 has 2. 3p6. 4 has 2. 3d2. Okay, look at a periodic table. It's important you're looking at a periodic table now.
Is it always 1s2, 2s2, and then?
Yes. Now, going from left to right, when you look at energy level 1, I don't remember, do your periodic tables have the 1 through 7 on the left?
Yeah.
Okay, so when we started at period 1, we have 2 electrons. The first thing we fill is 1s2. Are you all clear why this is the first piece of our electron configuration? You have to start from the bottom, the least amount of energy. You can't just start adding your 8th electron. You have to start from the beginning. You have 1 electron. What element is it?
Hydrogen,
it's hydrogen, then
helium.
helium. Once I have hydrogen and helium, I'm at 1s2.
Is helium an S?
Yes, it is, because the first sublevel, remember, only has an s orbital. And it's different. If you'll recall, I said all the noble gases except helium have a p6. Helium, in the first energy level, only has one orbital. It only has the s sublevel. So once that s sublevel has 2 electrons, it's full. It is a noble gas. It is as stable as a noble gas because it filled up its only orbital, which was a single s orbital.
Wait, so is hydrogen alone 1s2? Or is it?
No, hydrogen by itself would be 1s1.
Okay.
Two electrons.
Hydrogen would be 1s1.
As you go down the table, like from 1 to 7, you like they have so earlier you were talking about how orbitals exist so electrons in them
Yes.
or not, but like hydrogen only has one
Yes.
orbital, whereas like sodium has 4 orbitals.
Yes. Yes.
So does hydrogen just have a half orbital then?
Hydrogen has only one orbital, an s orbital.
Okay.
Yeah.
Can you explain where the subscript comes from again?
The superscript? I can. Okay. Now, after we fill, following your periodic table from left to right, we're done with the first row. Do you agree? So go down to row 2. What is the first sublevel in the second row? It's the 2s, correct? And if I wanted to write just for lithium, think hard, are you listening carefully? If I wanted to write the electron configuration for lithium, it'd be 1s2, 2s1. In fact, everything in the first row in row 1a in your periodic table, its last piece will be s1. In group 2a, the alkaline earth metals, it'll end in s2. Now my 2s is full, what's next? Move to the next element, which is boron, correct?
Yeah.
Boron through neon is what sublevel?
2p.
2p, and it's full, because I gotta go all the way to 22. Got that one? True or false? The second row is full.
True.
True, we're at neon. Go down to the third row. What's the next sublevel for sodium and magnesium?
Yes.
Am I having sodium and magnesium?
Yeah.
Yep. It's 3s2. Are you good to there? What do I fill up next? Keep going. 3p is the third row done. Yes. What's next? 4s2. And what's next?
4d.
Think hard. What did I tell you about the D's?
4d. Skin.
It's 3d,
Skin.
2. And I knew it was 2 because scandium's 1 and titanium's the second one. Do you agree?
Yeah.
Okay? Yes.
Can you explain again why we go from 4s to 3d rather than?
It's energy. When you look at the energy, I gave you what the energy is for the orbitals in that alpha chart.
Okay.
And I'm telling you, and it's true, when you look at that chart, do you remember when I was holding that ruler and you were going up? The 4s is lower energy than the 3d. And you don't even need to memorize that because it goes in order. The 4s is before the 3d up here, isn't it? So I have to do.
So then does 3D end at C?
Yes.
Okay.
When is it F?
F inserts right where that star is.
Oh.
It inserts in row 6.
Does it insert to the right or to the left?
Look at that periodic table up there. I have that periodic table, and I have a comparable, the same periodic table over there that's spread out so you can see where the F sublevel inserts.
So then you just add the ones, all the ones that are in the, like, this, well, you just add them all together and you have like just a huge amount of numbers
Yes,
that can
and we're gonna practice some of those. We're gonna do
Okay.
some of those together.
So the first, not like the 1, 2, 3, 4, does that not have to do with the numbers corresponding on the left of the periodic table? It's the energy level?
Yes, they do. Those numbers on the left, the 1 through 7, for the S and the P sublevels, that is the energy level. So if I say 4S, it's in the 4th row on the S. If I say 6P, it's right here. For the D's, the energy level is N, that 1 through 7, minus 1. For the F's, it's N minus 2. That's why in the 6th row, when you look at 56, 57, and then we go 58, 59, what's 6 minus 2? 4. So we have the 4F sublevel. And I will practice those with you, and we will go through them one piece at a time. Yes?
So when you insert that, like that bottom row in there as you would in an extended one, why is it that scandium and yttrium moves over to the right, but
I don't like the way they did this periodic table, that's why I put that up there. That's the way it's set up.
okay.
Would you like us to memorize the graphic? Just like it's
Which graphic?
like the chart that you fill up with the arrows.
No, you really don't need to, and when we practice this, you're gonna see why.
Okay.
You really don't need to memorize it.
Alright.
Okay, here's this. Wow, Dr. Cotton, you amaze me. Okay, now, this shouldn't take you very long. What are you gonna do? What's the only thing that'll be different?
Add 1.
3D3. Cold
Where's
teams?
go wide? Okay.
Come on. It's a good day.
Oh
I have a presentation.
Okay, guess what I'm gonna put next?
24.
What do you think?
3, 4.
Well, that's what you might expect, except you'd be wrong.
That's not fair.
Life isn't fair. Now, folks, this, I'm going to put this up here.
Wait.
I'm going to put chromium's expected. Chromium's expected electron configuration
Yeah.
ends in 4s2 3d4. Do you agree?
Yeah.
So it's got, I'm just gonna write a 4s with 2, and it's got a d with 1, 2, 3, 4. Are y'all good with me so far?
Yeah.
You know what's gonna happen here? Do you know?
Is it Hun's rule? No. I mean, this was.
Sort of.
Oh, we need to fill out the rest of.
Is it only half filled?
Which
The
one?
big tracking? On the one on the
You know what this wants more than anything?
Another one.
I would like, and you know where I'm gonna take it from?
So,
4S.
like, kind of.
But it reverses.
So I'm gonna end up with a different, it's gonna be the same thing with a 1 and a 5, because now I have 2 half-filled orbitals. And you can trust me when I tell you that D4 will steal 1 from the S to become D5. And you wanna know another one? D9 will steal 1 from the S to become D10. Yes?
Okay.
No.
Oh,
So did you reverse the spin when you took it over?
No,
Because it was a down
It-
arrow and you turned it into an up arrow.
it wouldn't have mattered which one I took.
Okay.
It wouldn't have mattered. Yes.
So if we went on to manganese, would it just also add 1 back to the 4s to the
Yeah.
2?
So how do you know when to do that?
D4 and D9.
Okay, D4.
That's all you have to know. Yes.
How, like, can electrons change their spin? Or can that spin be?
I don't know the answer to that. It's more of a quantum set of numbers. When we start writing quantum numbers, it's more something that we are going to do. It is a thing, but face it, we can't see electrons. We can barely see an atom, and they got to be big. So we don't really see electrons. Okay, so look at this one. Yes.
Would like F14s take one from?
The F's are beyond the scope of what we're going to study in.
But like, would they
Yes.
take one from the S?
Yes.
Okay.
Half full is slightly lower in energy. So the same thing is going to happen with copper. Please look at this electron configuration. Do you agree that that would be my expectation for copper?
Yeah.
But what do you see would be a happy fix?
3d10.
Yes. So there is the actual electron configuration. And we call these exceptions. So if you ever see a D4, and I'm saying, is this the electron configuration for something that ends in D4? No, it's not, because that will go take one from the S to get two half full.
Two things. Will a D4 or a D9 take one from an F1 you could use?
No, just from the 4S. The 4S if it's a 3D, the 5S if it's a 4D, the 6S if it's a 5D.
But like, will it? That's another question. But like, say you have 4S 3D9. I mean 4S1 3D9.
No, you can't have that. You would have a 4S2 3D8. It's not going to steal one to become a 9. Think about that for a minute.
So,
yeah, think about it a minute. Yeah.
So is P5 just not strong enough to take one from the S2?
It's not.
Okay.
It's not. The only things that do that in reality are the D's and the F's. And our only concern, in regular Chem 1, you only have to do chromium and copper. You guys have to do all three of these D's. You know, I just added two more. But it's still the same thing. D4 becomes D5 and my S2 becomes S1. Yes?
So will there never be a situation where it's D9 or D4?
Correct. Okay? Very good. We're almost ready for practice.
We're almost there.
Okay, so there's your configuration differences, or those are your two exceptions. There they are. Just because you forget, so Dr. Cotton likes to do this. And I don't think I need to do light today. Let me look. Energy levels, quantum, atomic orbitals, quantum numbers. Okay, now we're gonna watch orbitals. And I will maybe. Come on. Okay, this is it. Chair dance. Chair dance. Okay, I'm gonna back this up. Okay. Folks, this, I'll put this down. This is an XYZ coordinate system. You all know what that is. This is a spherical S orbital, and that represents an area that's been mathematically determined to be, or I guess a volume, where it's been mathematically determined that we have a 95% probability of finding an electron a certain distance from the nucleus. So this area, mostly in the outside of this sphere, are where the electrons for hydrogen and helium would be found, in that area. And once that's full, then my first sublevel's full. Got it? So let's keep going. Okay, this is what p orbitals look like. I'm going to stop this.
Sounds like someone's playing somewhere.
So they do X, Y, I can't read. This is X, Y, Z. Now against each one of these, they've got them different colors. Let's look at the Y. This is a p orbital. It can hold 2 electrons. They could both be right there. You could have one here and one there. They could both be back over here in that piece. Or am I looking at the wrong one? These two. I could have 2 here, 2 here, 1 here, 1 here. I could have one a little ways out of here. I have a 95% probability of finding it in one of these two. When we look at this, if we could unsuperimpose these, we'd see that there's an area where you can't find it that's right in the nucleus, because those electrons can't go in the nucleus. Yes?
So they can like switch between them though? Like
Yes.
move, like teleport
Yes.
or whatever they do?
Yes.
Wait, so there's a chance that you could find 0 in the orange though? Like a
There's a
5%?
chance they could both be here, or one there, one here.
Just outside?
Yeah.
Okay.
But they don't teleport from orbital to orbital.
No, they are going to my Y, this is my, I'm going to call this my PY, because it's on the Y-axis. P subscript Y. So in this PY, this is one orbital. I can find 2 electrons in it maximum. They're spinning opposite directions, and they can be anywhere in these two. Both on one side, one on the other, you know, whatever.
Electron, so orbitals of the same energy or like the same principal energy level never overlap. Well, not principal energy, like
The sub, the
all
P's?
the P, yeah, of the same sublevel never overlap, but can different sublevels overlap?
Yeah.
Not in atoms. When they start overlapping is when we make compounds.
Okay, so within this a single atom they can't overlap.
Correct.
Okay.
Okay, so there, this is gonna show us a little bit more. Let's keep watching. And then we'll play the whole thing from start to finish. Now we're gonna add the D's, and there's gonna be 5D sublevel, 5D orbitals within this sublevel. This is one of those 5. How many electrons can this hold?
2.
2. This one can hold 2. These are the areas of probability that Schrodinger's equations have given us, where we have a 95% probability of finding an electron. They could both be here. You could have one here and one here. Even though there's 4 nodes there, all that represents is a mathematically determined volume of probability where we can find an electron. So that's complicated. Now there's 5 of these, so we're going to superimpose them when we're done. There's one. Oh, I should go back. You guys see why we called that one D and then it was XZ? It's because each of the nodes was on the X and the Z. So this one is called a DXY. They're all different. DZY. That one's D. Wait, no, that one's right on. And then look at this next one. This one's the one that drives people crazy. So those are the areas. I should back up just a minute.
Looks like a pacifier.
What?
So when you look at that one, those areas of purple, and they're not really purple, you know. Remember I said yesterday that drives me crazy because I give you these models and then you get this visual in your head. They're not all different colors. And these are areas of probability. And if you will look over here, right now, in this thing is where they're superimposing all of the d orbitals. And do you folks remember what transparencies were in overhead projectors? It's like I had those transparencies and I laid one down, and then I laid the second one down, then I laid the third one down that I just showed you for the D, then I laid the fourth one down, then I laid the fifth one down. So that's good. They're going to show us that in a moment of everything overlapping. Now they're going to put them all in, and I guess this is actually a 2S, or 3S maybe. There's the P's. Now it's going to put the D's around. So that, what you're seeing up there right now, is could be represented by the third energy level. If I had my electrons in there, I'd have 2 in my s orbital. I could have a maximum of 6 in my p's. Do you agree with that? And I could have 10 in my d's for 18 electrons. This is where my 18 third energy level electrons could exist. So it gets pretty complicated. I will never ask you to draw this out. But you will be asked to remember that s orbitals are what shape? How would you describe those? Spherical. And p orbitals are often referred to as dumbbell shaped. People call them dumbbells. But you know what I'm talking about? Can you visualize that? I see a lot of dumbbells. I don't really see how they fit that well, but that's what people call them. Should I blink at the beginning so you can see the whole thing? Okay.
What is this circle in the middle for? It wraps around that.
What?
For that final, was it C cube, DC cube?
Oh, wait.
Crash course
Cancel.
cancel.
Can't see it.
Cancel. It's under the button.
I'm just going back.
In the top right, hit autoplay, like hit the little blue dot or disable it.
Oh, right there. Okay.
Yeah.
I want to stop. What was your question?
The DC cube, what's the point of the donut shape in the middle?
I'm glad you asked that question. None of those things have a specific point. Those are the geometric shapes that have been defined by Schrodinger's very complicated mathematical derivations of what the shapes of orbitals are.
Okay.
That's all it is. They were mathematically determined.
Oh.
And they didn't do them on here, but I still have to show you the F's.
They have two.
Can you even imagine?
Oh my goodness.
Yes.
They have two like rings, right?
They've got all kinds of weird things.
Can you mute it, please?
Oh yeah. Let me go back one time. Now you can chair dance and sing. All my favorite things is chair dance, except you. Here it comes. You missed it. You have to say orbitals every once in a while. I don't really care.